We now have enough background information to understand this topic, regioselectivity in alkene addition. You'll note, as we've discussed thus far, that when I take an alkene and I react it with HX, such as HI or HBr, the hydrogen always ends up on the carbon that has more hydrogen stuck to it. And the X, iodine or bromine, always ends up on the carbon that has fewer hydrogens bonded to it. In this particular example right here, we can see that between the carbon to the left and the carbon to the right, the one to the left has more hydrogen stuck to it. Hence, our hydrogen from HI will end up there, giving me a CH2, whereas the iodine will end up bonded to the carbon that has fewer hydrogens, this one right here. It's important for us to remember that the reason this occurs is because doing so ends up going through the more stable carbocation intermediate. If I were to reverse the product, that is, place the iodine on the carbon that has more hydrogens and the hydrogen on the carbon that has fewer, I would have to traverse the less stable carbocation intermediate. Similar things can be said about this reaction. You'll note that the bromine ends up on the carbon in the middle, the one that has fewer hydrogens bonded to it, whereas the hydrogen ends up on the carbon to the right, which has more hydrogen stuck to it. Thus, the major products for each of these reactions are the ones shown here. This observation is called this reaction's regioselectivity. I realize that that word sounds a little bit confusing, but what it means is this. If I have an alkene, I have to ask myself, which region of that alkene is the H going to bond to, and which region is the I going to bond to? You'll notice that in each of these reactions there is actually a preference for one versus the other. In the world of organic chemistry, we often use the term selectivity to be synonymous with the word preference. Because this particular reaction is selective or has a preference for one outcome versus the other, that is, placing my hydrogen on one specific region and my iodine on another specific region versus the alternative, we say that this reaction is regioselective. That is, it has a preference for forming those bonds in one region versus the other. I want to drill this home by once again emphasizing, why are the major products shown here the major products, and why are the minor products the minor products? The answer is, once again, because forming the minor products would require going through a less stable carbocation intermediate. I'd now like to prove that to you by actually showing you the mechanism of one of these examples. This example right here, we've got the cyclohexene, and it's floating in a solution with HBr. Pi electrons are of course going to come out of this double bond and attack the hydrogen, breaking the hydrogen-bromine bond to release free bromide. The hydrogen now has a choice. Does it attach to carbon 1 or does it attach to carbon 2? Now, Markovikov's rule would of course dictate that it attaches to the carbon that has more hydrogens on it, which is carbon 2. Nevertheless, I'll show you both possibilities. If it attaches to carbon 2, then the carbon that ends up with the positive charge is carbon 1, as shown here. At this point, bromide comes down, plugs in the hole, forming a bond with that carbon, and gives us this product. Now, in contrast, if the hydrogen instead bonds with carbon 1, we end up with the carbocation being positioned at carbon 2. Bromide comes in, forms a bond there, and gives us this product. Question is, which of these two scenarios is favored? That depends on the individual stabilities of the carbocations. The one at the bottom is a secondary carbocation. The one at the top is a tertiary. Which of those two is more stable? The tertiary. Hence, this product in the upper right is going to be the one that will be the major product and the one that is preferentially formed or selected for over the product in the lower right.